As adds on to Lab 2 solution, I forgot to solve this with you. You may find it easy yourself, you can do, but just trying to solve it. So basically, you are given this hardwired motor control program. So it is connected electrically all. So now we need to change it by ladder logic program. So basically, we need to take the inputs and output and connect them to the input and output module interface of the PLC. And you write your program inside. So the connection, wired connection, all you don't need. So you do the ladder program instead in the PLC and you download it to the PLC. So how many input you have in this program? You have stop and start push button. How many output? You have 3 output: green light, red light, and a motor starter. So, or could be a motor, okay, directly connected to a motor. But usually this is a motor starter. And here is the overloaded contact, normally closed overloaded contact. You can put it as one of the input if you wish. It's up to you. Sometimes, and most of them, I ignore it in my programming. But also, you can take it and put it as one of your input. Alright, will be one of your inputs. You have 3 inputs: stop, start, push button, and overloaded normally closed contact of your motor starter. Also, when your motor starter will be overloaded, so then will be open, but in normal situation it's closed. So it will be open, and yeah, when it's open, so the motor will be de-energized, and then when the motor will be de-energized, then in that case what will happen if it is de-energized? So the green button will go on, right? Because it's de-energized. When it is energized, this will go on. So the light will be red. The red will be on. The red light will be on when it is energized. When electricity is passing through the motor starter, this normally open will close, and therefore the red button will go on. And this normally closed will open, and the green button will be off. But when it is de-energized, so the green light will be on. Okay. So I can consider 3 inputs and 3 outputs. And here is the seal-in circuit. Okay. We didn't introduce it like the seal-in circuit, but seal-in circuit means like because here is a push button. So now look to the okay. Look to the current. So now the current pass from L1 to L2 this way, and then it will pass here, but it cannot because it is open circuit. So it will pass here, but cannot because it's open circuit as well. So it's normally open contact, so it doesn't pass. So then the motor starter is not on. But when you press the push button, when you press it on, so then the current will go through, and this will be energized for a while. When this is energized, this contact will close. And now, because this is start push button is a push button, then it will, when you release your hand from it, it will go on again. So then, but the motor starter will stay on because now this contact is passing the current through it, and therefore it will maintain it on. Alright, understand? Because this is start push button. When you use push button, we often use a seal-in circuit. That's what we call seal-in circuit. So the output contact, you make it weak. This is a hardwired circuit. In ladder logic, we call this method a seal-in circuit method. Okay. And normally it's always recommended for safety reason, or may introduce it one time or may not, The start push button for safety reason is normally open, and for safety reason also the stop push button is always, we try to have a normally closed push button. So now when you are picking your input field devices for your system, try to choose your stop push button as normally closed for safety reasons. So maybe we will see more explanation about why it's for safety reason we use normally closed push button for the stop and normally open for the start. Also, I hope in other courses you also saw something, but now we focus more on the ladder diagram program. If time permit, I may explain to you some safety issues we consider when we are connecting input-output devices. Okay, for now, let's keep it this way. So you have 3 inputs and 3 outputs, and this is your program. You have stop, normally closed, normally open, and you have the overload contact. And that your system will look like this, normally closed. I replace it by a normally open instruction, or this instruction we call it examine if closed. Okay, that's why it's closed, so I examine. And the same examine if closed for the start. I use for the start examine if closed. It's open, so I'm not examining. Okay, overload, it is 1 in general. So then that's my relay coil equivalent. And here it is not M. So keep it the same, not M for G and M for red. Okay, but look to your push button. That's what interested me now. This is normally closed, not necessary to have here normally closed. This is very wrong, okay? So depends on your program. It should serve the function. If you do it normally closed like this, it's wrong. And now I am sure you're able to know why it's wrong. Right? So then you need to pay attention to this. Is very fundamental, okay? It is closed. You go to the data file and you will find 1 in the data file of this address. 1. So that's why it is on. Because here they will go to the data file and look to the status. So we'll find it 1, so that it's 1. It's a green, you see. Here is your program. You look at it. When your start push button is pressed and then it releases, stay on. And therefore the motor is off. When you stop, you see what's happening, okay? Also the overload contact you can work on. So you have 3 inputs. Even if you press the start push button, if you have overload on your motor starter, so it's not going to open. So then you protect your relay, okay? And also protect your motor if you have overload from it's a 3-phase motor, so it's very costly motor, right? So you protect your motor. Now there is no overload, so then when you press start, it will work. Okay. Yeah, that's it for this exercise. If you have a doubt on why normally closed and normally open, you still get confused, I invite you to watch the video or also to go again to your lab 2. Go again to your lab 2 and carefully do this exercises. Okay, this exercise, you have a normally open push button, press it and look to the data input file and see what it happens if you have connected to it a examine if closed instruction. Okay, do this exercise as well. Alright, and do this exercise, but with now a normally examine if open instruction. Okay, but it happens in this case. So if you understand those, then you are alright. So then you can go back to your problem. Okay, so you can look at them here. Like for example, here it is I04. This is the instruction, and it is normally open. If you look at it, this 1, 4, it is 0. So now when you press it, you open it, it is 1. So you see it is 1. Alright, so when you release your hand, it goes off, etc. Okay, now you can see this one as well. So same I4, but now your is examine if open. Because it's open, I examined, and my light is on. This is the examine if open instruction. So it is 1. So then it will save in the data file, it's 0. So it's saved in the data file 0. Then 0 here will be not 0. Okay, so it is 1. So examine if open. That's why you call it examine if open. See, when you close, it is 1. This is examine if open. Now it's closed, so don't examine. Or you can see now this address will go here and see what do you have here. They will find 1. Then this is the instruction is not whatever here. Not 1, so it's 0. That's why it is off. Okay. Maybe let's see if there is any other stuff useful. Okay, this is normally open as well. Maybe try to find something is normally closed. Okay, let's see. Like in here, you have normally open and normally closed push button. You see, but it is I1, so it is closed. You see, it's closed. So that's why in the data input file you have 1, and it is P2. So when you go to I11, it will go I11 address will go and look what do we have in my store. In my stored memory about the input 1, 1. So I have 1 because it's normally closed. And this is examine if closed. So it is 1. So then you see here 1. Alright. If it was not, then if whatever I have here, if it is 1, so you'll get 0 here. Okay? Hopefully you don't get confused about that. That's it. Actually for lab 2, also I forgot to present to you some instructions, like, but they are easy. So like the AND instruction, you have a function block called AND, so you'll find it, so you can use it to add two sources together. Like I have them in the memory in B35 and in B37, so I add them together. Okay, so when this switch is on, so I add whatever is in source A and source B, and I put them maybe in B310. I put them here. Okay, so when the switch is on, I added them together, and the result is in here. Okay, this is the result of adding these two numbers, 35 and 37. Alright, so it is AND multiplication, like multiplication. Okay, so you get that number. course, when you say off, it's already added, so it's saved in the memory. So that's it. Also, you have the OR instruction. Same. I put in destination, so 1, 2, and 3. 1, 2, and 3. So now it's a OR, so OR like plus logic operation. From this you get the result of adding this plus this. Of course, when you go off, it keeps saving the data. The two remaining one, you have the XOR. Also, it's a logic operation. XOR. Here, I'm getting source A is input 1 and source B is input 3, and the destination is on output 4. So I'm here representing the XOR. So you can represent the and OR for bits, for inputs, or even for memory. Here, like they did the example for taking two input as source. Same you can do with for AND and OR that we saw in a while. Okay. So now, when both are on, so your output 04, let's see, I1 and I3. Okay. I1 and I3, and this output goes on, output 4. Okay. So this is XOR. XOR functionality. This is I3. Okay. So taking one bit of it. If you look to I3, don't get confused. So here they are taking I1 as the whole here actually. And when they said 04, they're taking the whole stuff here. So I3 is also taking the whole stuff. So I1 XOR, if you wish, I3. So it's 16 bits. So we add them bit by bit. And then we look to the output as 16 bit. Alright. Here what they are doing actually in this exercise. But also you could take a bit, only a bit, not like a word which is 16 bits. Up to you. See, 1 plus XOR 1 is 0. 0 XOR 1 is 1. 1 XOR 0 is 1. 1 XOR 1 is 0, etc. Okay. So we understand it now. Okay. The last one is NOT. XOR and NOT. So here you have a source binary, which is your memory. It's just an address in the memory to save data on it. So you save B10, and here it gives you the destination in 39. Destination is 310. It's not 1, so 0, 1, 1, 0, 0, 1. Okay. And here you can see them in decimal. So it gives you the NOT of it. Yeah, those I didn't present them to you in your lab. They are easy, so you can just, I forgot actually, but they're not necessary. That's it. I want just to go with you over This is 8 minutes video in case you didn't see them, so you watch them with me now. This is basically about your data sheet. If you remember your data sheet, when we're talking about specifications, so here you see the Siemens PLC similar to the one we have at the lab, slightly different, but so at least you can see it in a video because we don't have the chance to see it at the lab. Okay.
Hello guys, welcome to NFI online video tutorials. My name is Rajveer. I'm one of the educator in NFI. Now in this video we are going to learn about introduction to PLC. We are using a PLC named Siemens S7-1200 with the CPU 1212C AC-DC relay. And in this layout of videos we are going to understand the PLC hardware. We will see how the processor works, and we will wire the inputs and outputs. We'll understand the basic fundamentals, how to wire this PLC, and then we'll have a summary. So I'm using a PLC S7-1200 along with these tutorials which you can see on my table over here. So this is my PLC which is powered up, and using this PLC on my desk I'll explain you various things how to work with this PLC. Alright, so let's start. The first lesson is understanding PLC hardware. So that's the same PLC we have on the table, S7-1200. So let's see what are the various elements in this PLC. So we'll start with power supply 120-220 AC. Now this power supply of this PLC has to be provided with 120 or 220 AC.
So you connect it to the main sector
From your power source. Now you may find some PLC in which we supply 24 volts, but this one is AC input voltage. Okay.
As the one you have at the lab, so it takes AC input voltage.
Now why? Because this PLC has an internal power supply inside. So if I show you this one, this PLC, if you see this part of the PLC is the power supply. So this part converts the AC into DC. So you don't have to use any external power supply in this case. You can directly provide AC voltage to this PLC. Okay, so you must take care of that, because if your PLC is DC source, if your PLC is written 24 volts and if you provide AC source, it will burn out immediately. So you have to check that. But what is the power supply rating of your PLC? Okay, so this is provided over here. So in my PLC you can see some wires. This is the wire. This is coming out from my power source, and this is giving me line and neutral of 220 AC. So we'll see its more details in the next slide. Now next we have digital inputs. Now you know that PLC is a digital controller which converts your input signals and process that using your algorithms, and it will give you some outputs. So digital inputs are connected to this part of the PLC. Okay, so this PLC supports, now that's the model number, this PLC supports 8 digital inputs, and these digital inputs is of 24 volts, and you have to supply it here, and correspondingly you'll find some indicators.
So they told you this digital inputs are of 24 volts. Okay, so let's repeat.
And these digital inputs is of 24 volts, and you have to supply it here.
So you supply 24 volt in here. Yeah.
And correspondingly you'll find some indicators. Now these indicators will tell you which input is on or off. So we have some green lights here which will indicate the input is on. If there's no green light, it means input is off. So I can show you by having a look at this PLC. Now this is my input simulator.
So this is an input simulator, so usually switches just to simulate things. So you can use on-off switch, like in our input-output simulator. We have switches, but we have push button, we have a pressure sensor, limit switch, etc. in our Logic Pro simulator. Here it is just a simulator for push button, or you can simulate this switch. If you want to use your switch as a push button, you press it on, then you turn it off, and that's what we was using in our lab usually. If we simulate a push button, or we connect a push button in some other places. Anyway, here they have 8 input. So, and if your PLC is 8 inputs, so you you cannot connect more. Maybe our PLC had more, so I was able to connect even more inputs. Okay, so I can simulate push button alone, but also you can simulate the push button by a switch. How? So you press it on, then you turn it off again, as if you are releasing your hand from it.
If I turn on the input, you can see that if I turn on this button, it shows my third input is on. Okay, this is how input is indicated on this indicator. If I turn on another input, it will show my first input is on. So this is connected to my inputs. So how to wire this input, that will come later in the lesson. This is just to understand that we have an indicators here which will tell you about the status of the inputs. Okay. Next we have digital outputs, and it says 6 number of outputs, relay type.
So see here you have in this case 6 digital output, relay type. Hopefully he's explaining relay type. Let's see. And relay usually means AC DC, so you can connect AC load or DC load at the output. Okay.
Now relay is a coil which has some ampere ratings. So there are two types of PLC outputs. One is transistor type. Generally it's two types. One is a relay type.
So you have actually 3 types. You have relay type, and you have triac for AC, and you have transistor for DC. If it's a relay type, means it supports DC and AC load. So on your digital output you can connect an AC load or a DC load in this case.
So relay type has more current capability than transistor types.
For example, so you can have more currents load.
So we have relay types output here. We have 6 outputs. Okay, and then we have digital output indicators here. So similarly, the way we have seen the LEDs for inputs, we can have an LED for outputs. I could have shown you that, but my PLC doesn't have any logic inside. But in later lesson, you will see how you can see the status of your outputs on these LEDs. So if you are turning on, let's say, a lamp or a solenoid or a motor, even you can see their status on the PLC. Instead of visualizing them at a physical level, you can see their status on the PLC as well. Okay. Then we have PLC status indicators. Now status indicator means whether the PLC is running, or is it stop, or is it at some error status, or is it at some maintenance mode. So this is a status indicator. So currently if you see this PLC, it shows my first LED is on, which is my run LED. So PLC is at run mode. At run mode, it will start executing the logic and it will give you the output. Okay, so this is a typical layout of a PLC. We have power supply, inputs, indicators, outputs, indicators, and status indicators. So as mentioned, we have different status, run, stop, error, and maintenance. Okay, so let's proceed. This is a zoom layout of your inputs. So starting.
So let's look at them. So this is your inputs. Okay. So he may probably show you how to connect input devices. Okay.
With this, if you see here, power supply, this is L1 and N.
So L1 and N is your power supply. So you get it from your main sector. You see this white cable is connected to L1 and N. Okay, this is your, and then it will be converted to, you see, they telling you 120 to 40 volt AC. Then it's connected, so the output of this power supply, because here you have inverter, AC to DC converter, output is L plus M, and L plus M is the 24 volt DC. Okay, L plus and M like ground. Okay, just 2 second 2 pins. Let's continue.
If you see this symbol, this arrow goes downwards. Now this means you have to supply the power. Okay, it's mentioned 120 to 240 VAC. You have to supply AC voltage inside it. And this X10 is the dedicated number for these 3 terminals. This is the symbol for earthing. Now if you see these 2 terminals, it says L plus and M, and this arrow is going outwards. This is the DC output, which is 24 VDC. We will get 24 voltage output from this device. Remember that you should not have to provide 24 from the power supply. It will give you 24 volts. Okay, we can use this 24 volts for wiring our inputs, which we'll see that in the later slides. Then you have these terminals, 8 terminals for your digital inputs.
So we may see how they are wired in the next slide, as he said. So we have digital input, 8 digital input from 0 to 7. So those are, if they are from 0 to 7, so how many you have? 1, 2, 3, 4, 5, 6, 7, 8. So why I have 10? Okay, so from 0 to 7 is 8. Just 2 for the in, just 2 for the out. So you may have a 1 ground then. Okay, so let's count from here. 1, so 0, 1, 2, 3, 4, 5, 6, 7. So let's see, 8. From 0 to 7 is 8. 1, 2, 3, 4, 5, 6, 7, 8. So why is 10? Why is 9? So one more, what's this? Let's see.
To connect your digital inputs. Then you have analog input as well. So this PLC supports 2.
So he's not talking about, but telling you like you have 1 ground. So now if you want to connect the switches, the switch, so you can take L. So here is ground connected to 1M and M are connected together. This pin and this pin are connected internally. So what you do, you take from here to the switch and the output of it, you take it to your pin. And usually you have 8 pins. So maybe other pins are not used. Some other pins are not used. But you have here, you can connect 8 digital inputs from 0 to 7. And those grounds are connected internally. Okay, digital input DI8. Okay, so here they are talking about analog inputs. So here you have 2 analog inputs. Also, this analog input 2M, when they said 2M, it's also connected to the ground, like first ground, if you wish, second internal is connected to the ground, and these are the 2 pins for your analog input device. Okay, then maybe here is not mentioned, we will see, is it current or voltage analog input? So my sensor could provide analog current signal or analog voltage signal. So the one we have at the lab, it receives 0 to 10 volt analog voltage signal. So you should have a sensor that provide a voltage source, not analog, not current source. And we always know if we have a current source, actually we can convert it to analog source by passing it through resistance, and therefore you get the voltage source.
2 analog inputs. One is at 0 and 1. Okay, so it has 2 analog inputs, and what are the resolution? We'll see that in the later slides. Then you have a memory.
Of course, resolution is important, as I show you in the links video. So resolution, number of bits, as higher as they are, as your accuracy is more. As the smallest step change detected is smaller. Okay, so you can detect small step change in the input.
Memory card slot. Memory card slot is to store some information of your, let's say if you're recording some values in your PLC program and you want to store that value, and later you want to read that value, you can keep storing that value in the memory card. This will help you to have a record of your process. Alright, then we have outputs. This is the output terminals of the PLC. So starting with communication status indicator. Now if you see here, it says link and RX and TX. So if your PLC is connected to some, let's say an HMI or some other device which supports RS485 or Ethernet communication, this LED will show you the status.
So these are communication status indicators. For example, our PLC is connected, the one at the lab, connected to human machine interface HMI via Ethernet cable, and therefore those wiring are connected. So let's hear again.
PLC is connected to some, let's say, an HMI or some other device which supports RS485 or Ethernet communication. This LED will show you the status. Okay, so this is the status to ensure the communication is perfectly fine or not. Then you have a LAN interface. So this is one of the best feature of S7-1200, that you have a LAN interface. So you can program your PLC with a standard LAN cable. You do not need any other programming cable, unlike S7-200 or Micrologic's 1000, which does not support LAN. So this PLC supports LAN, so you can use your standard LAN cable to program the PLC, which is very easily available in the market as well. So this is a MAC address of your PLC. Then you have these relay outputs as mentioned before. So you have 6 relays output which you can connect to these terminals.
So in this you have 6 relay output. In ours we have 1 analog output as well. Yeah, so I don't remember if that analog output we have at the lab it is current or voltage. So the signal going out of the analog channel of the PLC, is it voltage signal or current signal? I don't remember, but we have 1 analog output, so you can have an analog output field device to control. I'm pretty sure what the one we have is between 4 to 20 milliampere, I believe. It's a current analog output signal. Not sure. So here you have 6 digital output. So you can see 0, 1, 2, okay, 3, 4, and 5. Yeah, so 0 to 5 is equal to 6. 0, 1, 2, 3, 4, 5. And this and this are, so this is your pin, and this is the output. Output source. So here you put your power supply. So here you may need a power supply. Okay, if it is a DC load or it's AC load, depends on your load. What is it? Assuming it's DC load, then this is connected to DC, and the ground will be connected, for example, if assuming here is a light. Okay, at pin 0, that's a pin 0. Here is a pin 0. So that's your circuit. What happens is, because this is a relay, so when I give order your program to close this relay, what happens is this relay will close, and therefore you will complete the circuit. Okay, so relay, you can put any voltage here, depends on your load, but make sure that the current driven consumed in total, for example, in our case, should be less than 12. Good.
So you have 6 relays output which you can connect to these terminals.
Yeah, I think that's it.